All right, guys, so section 1.3 here, I'm going to be dealing with absolute value equations and inequalities. So let's just kind of go back to basics here, start with basics. What does absolute value even mean? A lot of times when I ask the question, what is absolute value, students will always say, oh, it's always positive. And yeah, that's true. And really what it means, it's always positive because it is actually a distance from 0 on a number line. Okay, and when you measure distances, they are always positive, right? You're never going to be, negative 36 feet from something. You're 36 feet. So since it's a distance, it's going to be a positive value. So when we look at a simple, a real basic equation involving absolute value, like the absolute value of x equals 3, it's really asking yourself, it's asking you which numbers are 3 units. This is that distance, in this case from 0 on a number line. So if you think about if you're on a number line here, if 0's in the middle here, you're 1, 2, 3 units away that way, or 1, 2, 3 units away that way, right? Aren't both of those values, isn't that distance 3 units? And from 0 to positive 3 is also 3 units. So the values of x that would work is x could be 3, or x could equal negative 3, right? Both of them have that distance. It's just one of them is like a negative distance, kind of, or like to the left, I should say, and the other one is a distance to the right. Okay, so if you were to plot that on a number line, which it'll have you do sometimes, you would just put dots at at negative 3 and at positive 3. Those are the solutions to the equation. Okay, so let's look at a couple more. When it gets a little more complex, sometimes you just got to do a few steps, but that's kind of the basic, mindset on these. All right, so now we're getting into the Springboard book here. So this will be page 11. The PDF is in Schoology for you guys. So basically, we want to talk about solving these as they get a little bit more complicated, and then we will get into some inequalities as well. But first off, it's talking about the definition of absolute value to solve these, and it looks really fancy. It looks kind of complicated, but really all it's saying is if you have the absolute value of something, right, like this ax plus b here, it could either equal itself, okay, like when we did the previous example, the absolute value of x equals 3, x could equal 3, right, or x could equal the opposite of it. It could equal negative 3, right? And when we did those previous examples, those were the two answers we got. So that's really all that's saying as far as by definition. Let's look at a couple worked out examples. There's example A here. You can kind of see 2 times the absolute value of x minus 1, and then the minus 5 there equals 1, and they want you to solve that in graph. So if you notice the steps they're doing, these first few steps here, are trying to get that absolute value expression by itself. Okay, just like when you solved in Algebra 1, when you solved basic equations, you did what you had to do to get the variable by itself. So the first things they're doing is getting the absolute value by itself. So they first had to take care of this minus 5, so they added 5 to both sides. So you see in the second line, it's 2 times the absolute value of x minus 1 is equals 6, right? Because 5 was added to both sides. And then the next step, that 2 out front is actually saying 2 times the absolute value of x minus 1. So when you divide both sides by 2, you get to just an absolute value of x minus 1 equals 3. So now you have the absolute value isolated, right? There's nothing on the same side of the equation. So now's where you're ready to use the definition and say, okay, the x minus 1, okay, the stuff inside here could either equal positive 3, or the whole x minus 1 could equal negative 3. And then you just solve each of those individually by adding 1 to both sides, and you get your 2 answers. Okay, and to show them on a number line, you just simply put the closed-in dots at negative 2 and at 4. Okay, all right, so let's do a couple on our own, and let's walk through all the steps. All right, so there's a few examples here. Let's walk through. We'll start with example A. And I'm going to apologize for my writing. It's a little bit sloppy with the stylus. I'm still kind of getting used to it. All right, so the absolute value of x minus 2 equals 3. Okay, this is example A. So we got to ask ourselves, is the absolute value isolated? Okay, is there anything else on that side of the equation that's outside the absolute value bars? And in this case, the answer is no, right? So it's is yes. It already is isolated. There's nothing else out there. So what I'm going to do is I'm going to take whatever's in here, okay, the x minus 2, and I'm going to say that could either equal 3, okay, or the x minus 2 could equal negative 3. Okay, so I kind of split this up into two cases, right? That definition said there's two options. So when we add 2 to both sides, we should get answers x equals 5. Okay, add 2 to this side, x equals negative 1. Okay, and those, we can check them. Let's check them, especially we're first starting out here. So if we wanted to check them, how do you check an equation? You always plug it back into the original, right? So let's check, if I checked x equals 5, if I want to check x equals 5, what I would need to do is plug that into the original. So it said the absolute value of 5 minus 2, does that equal 3? And I like to do a little question mark when we're checking things out. And so if we start simplifying, 5 minus 2 is 3. Is the absolute value of 3 equal to 3? Okay, again, is 3 units away from 0? Yes. Okay, so that seems to work. Now here's the other one that might not have been as obvious. Does negative 1 work? If I want to check x equals negative 1, plug negative 1 in. Negative 1 minus 2, so the absolute value of all that stuff, does that also equal 3? So negative 1 take away 2 more is negative 3. Is the absolute value of negative 3 equal to 3? Yes, it is, right? Because negative 3 is also 3 units away from 0. So that appeared to work as well. All right, let's try another one. Let's do one of the hard ones at the bottom there. Let's do C or D. Let me give myself some space here. Let's do part C. So in C here, it said the absolute value of x minus 3 plus 4 equals 4. Okay, so in this case now we do have to do some work. We're not ready to split this up into two cases yet because I have that plus 4 sitting on the outside here. So we need to take care of that first. So I'm going to subtract 4 from both sides to get the absolute value expression isolated or by itself. Okay, so in this case we get the absolute value of x minus 3 equals 0. Okay, 0 a lot of times is a special situation, right? So when we get a 0 there, in this case, when we, so let me move that up a little bit. When we split this up now, it's always whatever's inside the absolute value bars equals the right side of the equation, or the x minus 3 equals the opposite of it. Well, the opposite of 0 is still 0, right? So in this case, we only get one solution. Okay, so in many cases, you're going to get two solutions like part A. But in this one, we actually only do get the one solution. So that happens, and that'll happen when you get the absolute value equaling 0. Okay, because again, think about which numbers are 0 units away from 3. There's only one answer to that. Okay, so let's do example D. I'm going to do it on the next page. It's the absolute value of x plus 2 plus 3 equals 1. Okay, so here's example D. So again, similar start, right? That plus 3 on the outside, we need to take care of that first. That's probably the biggest mistake I see on these is people want to just split this problem up into two problems. They want to set everything equal to 1 and then set everything equal to negative 1. And you can't do that yet, okay? Because this plus 3 is sitting there on the outside. So let's subtract 3 for both sides first. Now we get an absolute value expression by itself. And in this case, it equals negative 2. Okay, so the absolute value of x plus 2 equals a negative 2. Okay, this should be ringing bells in your head, hopefully. Remember, absolute value measures a distance, right? Can the distance, right, be negative? No. Okay, it cannot be happen. So if you get an absolute value of anything equaling any negative number, okay, like in this case, that means there is no solution to this problem. Okay, it's not possible to happen. Because again, we had absolute value by itself and we had a negative number. Let's just say, okay, I'm not, and this is going to be wrong, but let's just say you didn't notice that. Let's say you just went to the next step, which would be set x plus 2 equal to negative 2. and set x plus 2 equal to its opposite, right? And we did the two cases, and we tried solving it like we talked about before. Okay, when you subtract 2 from both sides, let's say you came up with two answers, x equals -4, x equals 0, right? And you left those, okay? Those are clearly, we said, wrong because there's no solution. You would find out they're wrong when you go to check it, okay? Because watch what happens. When we check x equals -4, if I put -4, the absolute value of -4 plus 2, and then plus 3, and ask ourselves, does that equal 1, right? I just checked it by plugging in the x into the original. So -4 plus 2 is -2, so the absolute value of that, plus 3, does that equal 1? So what's the absolute value of -2? It's 2. Okay, is 2 plus 3 equal to 1? Heck no. Okay, so you could always come up with your answer by checking it, and it's always a good idea, just in case, in case you don't recognize right away that, oh, that it equaled a negative over here, there's no solution. Okay, so just be careful on that. One more thing I want to point out to watch for. Oops, let me just throw one more quick thing that I just thought of. Let's say, let me just make a simple one, x minus 6 equals -2 or something. This is one other common mistake I see. People will see this and be like, oh, it's an absolute value, it equals a negative number, it's no solution, done. Okay, and that's not true, because in this case, again, that -6 is still on the same side of the equation. We need to isolate the absolute value by adding 6 to both sides. Now this one actually does have two solutions. Okay, so you can only go to the no solution with equaling a negative once the absolute value is already isolated. Okay, so just be careful with that, and you'll see some of those in tonight's assignment, I believe. All right, so let's look at like an application of this. Where would this stuff even apply, and how can it be used? So if we take a look, example B here in the book, we see the temperature of the wave pool at Sapphire Island can vary up to 4.5 degrees. So it can be 4.5 higher or 4.5 lower from the target temperature. So that should kind of remind you of absolute value, right? Absolute value is how much above or below a given value. So can we write and solve an absolute value equation to find the temperature extremes, right? What's like the highest it could be and what's the lowest? So the way this kind of works, as you notice, the 4.5, that's how much it can vary, right? We said that's what the absolute value can be, okay, or equal. So in this case, we're not varying from 0, we are varying from 82 degrees. Okay, so basically the temperature minus 82, if we take the absolute value of that, that needs to be 4.5. Okay, because again, it could be 4.5 above 82 or 4.5 below 82. So the absolute value, the 4.5, is the amount that it actually can vary. So we get our equation that's set up. Okay, we take a look. It's the absolute value of t minus 82 equals 4.5. So there's nothing on the same side of the equation as the absolute value. It's already isolated, in other words. So we're ready to split this guy up and take the t minus 82, set it equal to 4.5, or take the t minus 82 and set it to the opposite of 4.5. And to solve both of those, we add 82 to both sides. So we get our two values, okay? The temperature could either be 86.5, okay, or 77.5. That's giving you like a range, right? A maximum and a minimum value for the temperature. Okay, let's try and solve one on our own. Okay, try these B. So the pH of water is a measure of acidity. Okay, throwing in a little chemistry in here. Okay, so the pH of the water of the steel slide can vary up to, so 0.3 is the amount it can vary. That's what the absolute value is going to be able to equal, right? Because it can be that much above or below. And the target value is 7.5. Okay, so let's write ourselves a nice little equation. So it's going to be the absolute value of something equals something. Okay, and again, the amount that it varies, that's what the absolute value can equal. And we want it to vary from the target level. So the pH, I'm just going to use P, the difference from it and 7.5. So the absolute value of P minus 7.5 can equal 0.3, because we can either be 0.3 above or 0.3 below. Okay, so let's solve this guy. So it already has an absolute value by itself, so we are ready to set up our two equations. Either the p minus 7.5 equals 0.3, okay, or the p minus 7.5 equals negative 0.3. Okay, so notice I did not change this expression, right? When I wrote the two equations, the only thing that changed was that on one of them I made this negative. I didn't change the p minus to p plus. Okay, that expression stays the exact same in both. And then we can simply solve those by adding 7.5 to both sides. Oops, sorry, getting a little sloppy. So p could equal 7.8. Okay, or if I add 7.5 to a negative 0.3, that's going to give me 7.2. Okay, and that would be our answers. That's the extreme values where the pH would need to be between 7.2 and 7.8. I'm not sure what the unit is on that. I can't remember what that was. All right. Okay, second part of our section and the last part is instead of absolute value equations, right, with equal signs are going to be absolute value inequalities, right, greater thans, less thans. Okay, and I have a little method I think seems to work well with these. You may see something different in the book or whatever. If you want to try that, that's fine as well. But what I always think of, again, I'm thinking absolute value is the distance away, right on a number line. So in this case, instead of the absolute value just equaling 3, let's say the absolute value of x, okay, or the distance needs to be greater than 3. Okay, so let's think about this one's dealing with 0 since there's nothing inside the expression, no subtracting like the last example. So let's think about which numbers have an absolute value that's bigger than 3. So 1, 2, 3, 4, 5, negative 1, negative 2, negative 3, negative 4, negative 5. Okay, so in other words, which numbers are 3 units, okay, or which units are more than 3 units away from 0? So 1, 2, 3. So 3 itself does not work. Okay, there's not an equal sign under here, right? If you remember, inequalities can be greater than or equal to, okay? Or this one is just simply greater than. So that's why I'm going to use an open circle at 3, because 3 itself does not work, but any number bigger than 3 does work, right? Like 4 works. 4 is more than 3 units away from 0. 5 works. 6 works. Okay, 3 itself in this case does not work, because 3 is technically not greater than 3. Right? 3 is equal to 3. So more on that in a minute. And then in the same thing in the other way, does negative 1 work? No. Does negative 2 work? No. Negative 3 does not work, but it starts right there. Okay, because negative 4 would work, negative 5 would work. Each of those are farther away from 0. They're 3 units or more away. Okay, so the way we kind of write this, and here's what I always remember, the greater, I always kind of pronounce that as great or, and here's why. Okay, there's going to be 2 intervals of solutions. Okay, over here on the right, we have all the numbers that are greater than 3. Over here on the left, we have all the numbers that are less than negative 3. And it's going to be an or situation because you could be greater than 3, or the solutions could be anything less than negative 3. So my advice on these problems is this. Okay, take the problem as written. Okay, if it's a greater than problem, we're just going to, the first solution is just going to be to write it without the absolute value bars. Throw this or in there, and then you reverse the inequality and make the other part negative. Okay, so just like with the equations we solved, we made the right side negative. Here we just need to do the other inequality symbol, okay, which will be the less than. Okay, and we'll do a few examples in a minute. But hopefully visually we can kind of see why those solutions work. Okay, now the other case, the less than situation. Okay, let's draw it out again visually. Okay, so we got 0. Let's do 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so now in this case, I'm going to try and show all the numbers that are, their distance from 0 is less than 3. Okay, it's all those numbers, right? That distance, Like for example, the number 1 or 2 or even 3. -1, -2, -3. Each of those numbers, okay, -3 again doesn't work. -3 is like a borderline. But -1 works, -2 works, right? All of those numbers have an absolute value less than 3. So the issue is, how do we write that statement? Okay, now this case, it's going to be an AND problem. Okay, x is going to be less than 3, right? Because we're here and we're going that way. But it doesn't go on forever, right? We can't just leave it like that, because that would include numbers out here, -4, -5, -6, and those don't work. So in this case, it needs to be written as an AND. What else must be true about x? X must be greater than -3. Okay, and when it's an AND, it means that they both have to be true. Okay, and sometimes a simpler way to write that with an AND statement is this. You put the lower number first, then a less than sign, then the variable, another less than sign, 3. Okay, that's kind of saying x has to be like sandwiched in between, right? This is known as a compound inequality. So you can either write it with the word AND, or you can write it as a compound inequality, where it's saying two things. Okay, and if you kind of look at the two statements, let me see if I can highlight here. This was part of our answer, right? This was right here. Okay, and then the other part, this is kind of just written backwards, the same as this though, right? It's saying that x is greater than -3. The way we wrote it down there is that -3 is less than x, so those kind of match up. So I'm totally fine with however you guys want to do it. The compound inequality or the AND statement. Okay, so let's do a couple examples. All right, and again, in the book, you'll see there's a couple examples. They did one of each, and you can see the first one, and again, kind of getting this mindset of reading it as that's a great or, right? So that's an or problem, and you can see in the way they started setting it up as an or problem. And with the or problems, you get inequalities that the answers go in opposite directions, right? One's going to the right, one's going to the left. Whereas the second example becomes a compound inequality where the intervals actually go together. Okay, so let's walk through an example on our own and see how it looks. Okay, but feel free to read back at those at any time. All right, so let's do part A here. We have the absolute value of x minus 2 great or, right, great or, then 3. So since I know it's a great or problem, I'm going to set it up that way. I'm going to set up x minus 2. I'm just going to kind of rewrite it without absolute value bars. And then the or, x minus 2 less than. So I flip the inequality and I make that negative. Okay, so it's just like the equations, okay, except we had an inequality that needed to be flipped. Then we solve both. As normal, we're going to add 2 to both sides. X will be greater than 5. Or adding 2 to both sides here, x will be less than -1. Okay, and in this case, let's just get our number line together. Okay, the greater than 5, 1, 2, 3, 4, 5. Again, it's an open circle because 5 is not included. We'll do one, the next one we do will be included, and I'll close the circle in. But what I'm looking at on those, and I get questions on it quite a bit, I'm looking here, is there an equal sign underneath? And there's not in this example. That's why it's open circle at 5. Okay, and the other option to show this piece, x is less than -1, again, open circle, less than -1. Okay, so x could be either any number bigger than 5 or any number less than -1. They both solve the problem. Okay, let's try and do one last one. Let's look at example B there, which states the absolute value of x plus 2, we got a -3 sitting out there, is less than or equal to, right? There's the difference, the or equal, you got the half equal sign underneath there, -1. Okay, so let's kind of treat it like an equation first. Don't start splitting anything with it, whether it's an equation or an inequality before we take care of any terms on the outside. So add 3 before we do anything. Okay, absolute value of x plus 2 is less than or equal to positive 2. Okay, now we need to think about, this is not a great or problem, this is a less than problem. So less than is going to be an and problem, right? So I'm automatically thinking and, right? It's not great or, it's less than. So we're going to do the same thing. We're going to set it up, rewrite it as is without the absolute value bars. First, I didn't change anything. Then it's an and then the second one is where we flip the inequality and make the other side negative. Okay, and it's going to be an and. Both statements have to be true, and we'll talk about this when we graph it. But when we solve it, we get the variable by itself. X can be less than or equal to 0, and subtracting 2 here, x greater than or equal to negative 4. Okay, so let's think about the number line. 0's there, I need negative 1, negative 2, negative 3, negative 4. Okay, so we are less than or equal to 0. So I'm going to color this one in because it can equal 0, and it would go to the left. But this other condition over here says x has to be greater than or equal to negative 4. Okay, so it has to stop there. It has to be in between. And that's what the less than ones always do. They always look like an interval of numbers, kind of like there's a start and a stop point, right? Negative 4 to 0. It's not going, like if you look at the previous example went opposite directions, right? One went that way, one went that way, because it was an or. It was one or the other. This current one is an and. It's the numbers in between. Okay, and if you wanted to write that as compound again, we always just start with the minimum. It's always less than or equal to x, and x at the same time must be less than or equal to 0. Okay, that's how we write that as a compound inequality. That's probably the best way to write it. But the and works, and some problems may also have you do the number line visual display of it. Okay, so hope that helps. There's a few examples. For practice, I would like to, on page 14, okay, and again, the PDF is going to be in Schoology in this folder for you, or you can screenshot it here, I guess. Numbers 7 through 13. Okay, so we're not doing all these. We're skipping 6 and skipping 14. And show me all steps. It's going to ask you, the first ones are just solve, I guess, and then once you get to 11, they'll make sure we are solving and graph the solutions on the number line as well. Okay, all right.